So we are going to have a little bit of order, so you really want to, once you find something, please be quiet, otherwise this is going to be a really tough session to work through. You may remember that at one time, the next generation of science standards were on an interactive website. Well, that interactive website is back up on the Achieve site. So we're going to encourage you, when you want to go look at the next generation of science standards, that you can use that very nicely put together interactive website. The second aspect that Steve wanted me to remind you of is that the lead states only didn't send feedback via phone or email or whatever, but there was a very active process. The teams actually got together, came to Washington D.C., worked, met face to face. That was particularly true with the first 6 lead states, particularly true at Michigan, that there was a lot of back and forth face-to-face conversation. So it wasn't just a remote kind of process. It was a very close, interactive type of process. The last announcement that I want to make is that today you're receiving a lot of stuff, a lot of information. You're getting a lot of messages. And I want you to know that those messages are coming from the next generation of science standards. They're coming from the team that put all this information together. As of right now, they are not recommendations from the Michigan Department of Education. Right? The standards have not been adopted by our state. So these are all things that people working on this effort are putting forth as for us to consider and take into consideration, but they are not official statements or documents from MDE. I think that's really important to understand. So, Steve's going to chime in when he can add something. We're going to try to do this little interactive session, and we're going to actually try to really dig down and get you to understand at a much deeper level some of the ideas that Stephen already brought up. And so you'll see there'll be some redundancy. That redundancy was actually based on purpose. You'll see there's actually some sharing of slides, and that's because we share each other's slides. So, but it's all in the hope that we can go somewhat more deeper. So we're going to actually try to get a level deeper down. I'm sure that some of you, because of all the work you've done, already know some of this stuff. But because of the large number of people that are in the room, we're really going to try to get you to go a step down. So, what are we actually going to do today? We're really going to, it was just what I got done saying, we're really going to try to get you to understand by the time you leave here, both what the next generation of science standards are all about, but also to understand what that new term was that Stephen mentioned, bundling. So we're going to go this step down a little bit more. And this afternoon then, hopefully you'll really understand when you come out of your working sessions what we mean by bundling and how do you actually go about bundling. Because in some respects, bundling was the focus that you might say was our own learning goal, was to have you be able to use what bundling is. So Stephen stressed this a little bit, but I cannot give stand up in front of a group of people and not say this without going forward. And that is the next generation of science standards is for all our students. It's not just for students going into college. It's not just for, it's for every one of our kids. Every one of our children need to have the depth of understanding to be able to live successful and fulfilled lives in this world. That's what the next generation of science standards is all about. Yes, it will prepare them for college for those going into college. But every person has to really have this depth of understanding if they go into science, if they decide they want to go into business, if they decide they want to do something in restaurant management, they still have to really have this depth of understanding simply to be good consumers, to be good decision makers, to make intelligent votes. So I can't, that's what was driving all of us, was really trying to provide standards that really work for all students. So what's new? Stephen already talked about this, and I'm going to try to just go a little bit deeper into each one of these. So there's this notion of being around these core ideas. There's this notion of the centrality of scientific practices, the use of cross-cutting concepts, standards expressed as performance expectation, and then this notion about coherence across time, or how we have these various progressions. And so we're going to sort of highlight each one of those. So as hopefully by Stephen's presentation, the next generation of science standards are indeed different because they're expressed in terms of these performance expectations. And what I have to stress about this part, as Stephen did, but we have to, again, this is sort of the goal of what today is all about, is that for you to understand that performance expectations are what the kids at the end of instruction will be assessed on. It's not what we're going to be doing in our classrooms, right? We're going to have to think about how do we get kids, how do we get our students in front of us to really understand that stuff, right? That's what they can get assessed on. We have to then think about, as teachers, how we actually go from where they're at and take them up a next level. So they're very, very different because of that notion. And they're very different also because for the first time, we really have this blend of scientific practices, cross-cutting concepts, and core ideas that come together to express what the standard is. And hopefully you'll get to know a little bit about each of these parts, as well as what they mean when they actually come together. So, organized around core ideas. What are core ideas? So Stephen mentioned this, but I want to just take this a little bit further. And if you haven't, Stephen encouraged you to read the framework book. I'm going to actually encourage you as well. And it's actually not bad reading. You know, I mean, a lot of times we pick up these books and they're just horrible. We fall right to sleep. But the framework really isn't bad reading. Now, it's not like reading the Da Vinci Code, but you can actually pick it up and you can read it and you can learn something by it. So it's actually freely available. Again, my slides will be available. All you have to do is click your little phone on that, you know, your little smartphone on that little guy, and it'll take you right there. Or you can type in the web address. It'll get you there. So what's really important about them is that they're organized as sort of what's really important, right? So it's not everything possible, but it's actually trying to help kids through our instruction, through K-12, really trying to get them to have some conceptual tools. That's what the core ideas are all about. They're thinking tools, so that kids actually have those ideas in their head. They can actually use them to solve problems, to make decisions, and probably even more important, learn more. That's what the core ideas are all about. And so if you really want to start to have conceptual tools to help them have this framework in their mind that they can think with, you can't possibly cover everything. Because then what they're doing is they're learning just little bitty nuggets. And so the core ideas are actually focused on, can we actually get the kids so that they have these thinking tools? So you really want to, I don't have the framework with me, you really want to examine the framework on your own. I think you'll find it a very nice way of being organized for reading. So I would, if you don't read your own discipline, I would really encourage you to read your own discipline, but also look at the other disciplines. You really will learn a lot about what's going on in the other fields. So the core ideas actually have some really important characteristics around that notion, right? So if something's a core idea, helping your kids learn this notion, it actually gives them a lot of explanatory power. That's probably one of the most important criteria with respect to what a core idea is. So you could actually think of your own discipline, right? You could almost close your eyes and you could say, okay, what idea in my field really gives kids lots and lots of power to explain lots of phenomena? That's what a core idea is. A core idea is also really central to the discipline itself, right? It's really important. So you could, like as a chemist, Steve brought up the example. We can't live without understanding chemical reactions and particles. That's what we're all about. And the biologist, evolution drives the way a biologist thinks. An earth scientist is driven by understanding of plate tectonics. Those are all the big ideas. Now, I just mentioned them as topics, but they're really drivers. Energy, right? Every physicist is driven by the understanding of energy. It's just a critical concept. That's what a core idea is. And that's in our teaching, we have to actually think of them that way. Probably one of the other really important aspects behind what a core idea is all about is that we can actually help kids build an understanding of it K through 12. So we're not going to be teaching the same thing, but what in the grade levels, but we're going to go deeper and deeper and deeper and deeper as we build across the years, and I'll get a little bit more into that as we go on. So the value of them, because they are smaller, right, and they're actually not smaller, but there's fewer of them, they actually allow us as teachers to actually go into depth and actually do some exploration. That's why we can blend them actually with the practices. Otherwise we would just be covering content. But because there's this smaller set that really drives how we think, we can actually blend them with the practices and allow us to make, and this then allows kids to actually form what I like to call integrated understanding, which is actually kids actually forming connections between ideas. And it's that forming of connections between ideas that actually allows people to solve problems. So, Stephen, anything you want to add on core ideas? Perfect. Okay, so that's core ideas. And again, we're going to look a little bit at some of those when we look at the next generation of science standards. But I really want to encourage you to go look at the framework and trying to gain an understanding of what those are all about.
Hey, Joe, there is actually one thing. So one thing just to note, if you were paying attention to the development itself, from the very first draft that state saw to now, and I was actually just texting somebody back at the office because I can't remember the exact number, but we actually had cut over 100 performance expectations during the course of this thing. And we cut about a third between January and the release. And the reason I bring that up is because what we didn't affect were these core ideas. You know, the core ideas stayed. We didn't cut core ideas. We just made them more focused. And we also didn't mess with the progression. So in other words, if something was truly necessary for the progression, it stayed. So, you know, a lot was made about the fact that, oh, there was this big cut. There was, but what was actually, the way we made the cut was to ensure that these core ideas were clear and there wasn't a place where they kind of hit a snag and you kind of lost something. So I just wanted to throw that in.
So core ideas are, I don't need core ideas are central to a discipline, right? Energy to physics, chemical reactions to chemistry, evolution to biology. Cross-cutting concepts are the things actually that go across our disciplines. And they're very critical because they're partially the way, some of these are the way scientists think, right? Cause and effect is critical to what science is all about. We're always trying to find out what is something that really drives something to happen. Not correlational, but cause and effect. So it's having kids really understand what's the difference between having something that's a cause versus something that might be correlational. Looking for patterns, repeated patterns. Because it's these repeated patterns that actually give us our evidence that can allow us to support our claims, to allow us to develop our models. Then there's these other interesting things like energy and matter, right? Energy and matter, it cuts across all our disciplines and we can't escape it. And particularly energy, if you think about how important it is to every single one of our disciplines. But often when students, you talk about energy, it's, you know, it's a ball rolling down a hill. It's calculating some formula. They don't see it as really related to what we do in photosynthesis and respiration and how those things are so tightly connected. They don't see it in a chemical reaction. It's a different kind of energy than it's the energy in physics. And one of the goals of the framework, as far as the cross-cutting idea and the core idea, is to help kids to see that energy is actually one big unifying idea that really drives explanations across lots of phenomena. If we're going to do a little practicing with our book again, you can actually learn a lot about the cross-cutting concepts. If you go to tab G in your book, it's towards the end, and you'll see this is one of the appendices that are actually that's actually on the Achieve website, but it's in your book, so you should be able to open up back there. And again, this will make nice reading to allow you to understand a little bit more about what the cross-cutting concepts are all about. be able to go back to that one later on in your own. We're actually now going to get to a really important idea. If you think of core ideas and cross-cutting concepts, that's the stuff, right? That in some respects is the content. But content, as far as helping kids develop understanding, is not enough. If all we did was help kids try to develop these ideas, that's what they would have. They would have isolated ideas, and they would not know how to use those ideas in any kind of situation. And as Stephen said in his remarks, what the next generation of science standards is all about, and what the framework is all about, is actually knowledge and use. It's can we make use of that content? So the content of this is not enough. We actually have to blend it with the scientific practices. And as Stephen said, the scientific practices are the ways in which scientists and engineers actually study either the natural world or the design world. And these things also work together. Now, I don't have a computer in front of me, so I think you may have to press these buttons, but I'm not sure. Oh, no, I got this one. So these things actually work together. And as I sort of go through this, you might want to now go to tab Appendix F, which is actually the tab that talks about the scientific practices. And one of the things you'll notice when you go to the scientific and engineering practice, science and engineering practices, you'll see this idea of a progression. So if you just sort of focus on one of them, take whatever one you like the best. I tend to like modeling the best, because it tends to be what I'm into right now. And you can notice in the modeling progression how the ideas actually build across time. It's not that high school kids should be involved in modeling. And notice what this says here. It doesn't say just use models. As science teachers, we always use models, right? Especially as a chemist, you can't escape it. A biologist, you can't escape using models. But it doesn't say us use models. It says students will develop, construct, and use models. That's what it says. And if you look at that progression in Appendix F, what you'll notice is it's not just high school kids that are constructing models. The little ones are constructing models too, because there's lots of research out there that says that kids in elementary school, first, second grade, are capable of doing this kind of intellectual work. They're certainly not going to have as sophisticated models as we would. They may not have mechanistic models, but they certainly can construct descriptive models. And so that, again, shows you one of the major differences between what we did before and what we did now, is this notion of it's all active. In fact, if you look, these aren't only just connected, as I show. You may start off an investigation, or it might start off by people asking a question. Again, it's the student asking the question, but that might then drive to them obtaining information. Look at all those active words. It's students asking or defining problems. It's having them actually obtain and evaluate information. That may lead to the refinement of their questions, which then would lead to them designing and planning and carrying out investigations. That would then lead to them analyzing and interpreting data. These are all active situations. A new one for us is actually, and Stephen mentioned this in his assessment example, which I think is really important. In some respects, in science, we've gotten away from, if we're scientists, really, we think very mathematically. We create all sorts of wonderful relationships. But in our science classes, we've sort of moved away from that. It's very important for kids to have this qualitative understanding, there's no doubt about it. But it's also important to have them be able to think mathematically. That's not algorithmically, by the way, it's mathematically, right? It's not giving them a formula that they memorize. It's having them really understand what that formula means. And that formula actually is actually a model, right? So if you think of all of, a lot of the equations that we have that describe phenomena, it's a model. It can actually predict phenomena and future states. And so those are actually models. And that's how we have to help kids understand that, rather than having them think algorithmically. So once they do that, they may engage in argument. That's what we do all the time. We debate ideas, but we're always focusing on what's our evidence for that. that may lead to students developing and using models, which may lead to them constructing an explanation. Stephen, you want to answer?
Yeah, just a couple things. This is probably has the most empirical evidence behind it. You'll hear people say, oh, well, all those teaching strategies shouldn't be there. Now, these are things you'll use in instruction, but we have to know that part of the evidence that we've got for college and career readiness is ACT in particular. Their years of data collection has shown that kids being able to do this is a greater predictor of college success than kids being able to do advanced concepts. In fact, they did a white paper for us and very clearly said advanced topics are not actually good predictors of whether kids are good in science or once they go into either college or career, because ACT, remember, also has work keys. But these are actually very heavily empirically based. So that's one thing. The other thing is, we do have to just continue to stress to people, this is not, what you see in the standards is not dictating what you do in instruction, it's where we want kids to go. So these are outcomes just like content. And finally, let's face it, if we could get everybody to do these things, we probably could get rid of warning labels on products, because people can figure that out.
So again, these things work together, but I want to point out the active nature of these things, right? It's not us doing to students, it's students actually engaging these things. And of course, this may always lead to asking new questions. So you've seen a rope analogy from Steve. These ropes analogies are really important. I have this together to show that these things really work together. And not only do they really work together, it actually, by having them work together, it actually forms stronger understanding for the students. And the interesting thing is if you think, I grew up teaching in the early 70s to the late 70s, at least in the classroom. And we were always using inquiry to help the kids learn the content. That's an interesting way to think about it, but in fact, it works both ways. If we want kids to learn the content, we have to engage in the scientific practice. But if we also want the kids to learn the scientific practice, we have to engage in the content. They aren't separable from each other. These things work together. If you leave them out, if you leave one out, you really don't learn the other. You may memorize something, kids may be able to pass some kind of, memorized, test where they have to recall information. But if we really want them to get them to use stuff, if you want kids to be able to problem solve, if we want them to be able to analyze data, if we want them to be able to make statements and support those statements by evidence, then we have to have these things work together. That's actually, to me, one of the most powerful statements that comes out of the framework. So when Stephen said there's this vision aspect, this is the vision that they put forth. And it's not just a vision that we made up. It's a vision actually found on research. This is actually very solidly supported by much of the research that's out there. And so it's critical to have these guys work together. To learn one, you have to know the other, right? You can't do these in isolation. You can't do these in separation. It's the foundation. This idea is actually the foundation from what stems this architecture, actually, of the next generation of science standards. So, standards, these things all work together, so to form what we call these performance expectations. And the notion of forming standards is actually to integrate these and blend these together. So what you're going to see in front of you when you look at the next generation science standards, we didn't get this right the first time. The first round of feedback by the states was simply instrumental in helping us try to get the right structure and use. So in this case, if you really want to learn a little bit about that philosophy, you don't have to look at it now, but you can really look at your tab called the Executive Summary and the Introduction in the Next Generation Science Standard book. But you could, as I talk, you can maybe page there, because the idea was to sort of introduce you to all these resources here as well. So these ideas are pretty much there. Again, I want to stress this is knowledge and use. Right? This blending actually causes knowledge and use. So let's look a little bit about what we did as a team. So Stephen and I'm also, we keep talking about how these are integrated together. And so what that means is that we took a core idea, In this case, it's related to chemistry. Sorry, Steven's a chemist, I'm a chemist. You're gonna get a lot of my examples are chemistry because that's what I really understand and I feel more comfortable
I
talking
did do
about.
biology though.
What?
I did do
Oh, you
biology.
do biology. Yeah, I'm sticking with chemistry, I feel safe. So,
I was proud of myself.
so this is actually one of the core ideas. And, you know, it's not the whole core idea, it's just this sort of this part. This is actually related to middle school. Right? So this is a middle school section of the core idea, and so it's PS.B, PS1.B, and it says substance react in chemically characteristic ways. In a chemical process, the atoms that make up the original substance are regrouped into different molecules. All these new substances have different properties from those of the reactants. And then it says the total number of each type of atom is conserved, and thus the mass does not change. So these are two important parts. That is then blended with a practice. In this case, it's developing a model to describe underlying mechanisms, and then it's blended with a cross-cutting concept, patterns, so that the microscopic patterns are related to the nature of microscopic and atomic level structure, right? So it's this, again, that's that cross-cutting, that's a structure and function thing, structure and function. It's not only patterns, it's also structure and function one. So it was a little bit of we often wrestled a long time with which one we wanted to pick because they always didn't, which one was more prevalent. Those three then are blended together to form a performance expectation. So you have develop and use a model to describe how the total number of atoms does not change in a chemical reaction and thus mass is conserved. Right? That's the accessible part. The top three parts aren't accessible. It's the bottom part that's accessible. But it came from those three parts. And as teachers, as we think about our instruction, we can't just focus on this because if we just, and that's actually middle school, it should say AMS, it says MA, sorry, MS PS1-5, that's what that one is. And if we just focused on it, we couldn't just teach it. If you be able to just teach that without knowing all the other stuff, it'd be impossible, right? So that's the challenge that we're going to face. This is the accessible part, but we also have to help the kids know the rest of it that's involved. So this is what it actually looks like. And Stephen showed you some of this. And I'm going to try to, Stephen, do you want to add something to that with the architecture? So the architecture was actually a real struggle for the design team that sort of puts things together. Go ahead and say something.
Yeah, if anybody who's seeing that for the first time, or even the third, fourth, fifth time, let me just say, we all know it's visually difficult, you know, and we knew that going into it. But what we also felt like was just giving the list of performance expectations the way we've done state standards for the last 20 years, and then expecting all the teachers to unpack it, and hoping that they unpacked it the same, and then hoping they unpacked it the same as the people who were writing the test, just didn't seem like a good use of time. So the architecture was developed to be able to give, you know, I say all the time, if we had to pack it to write it, we just left the suitcase open so everybody could see what was there. And it was, from the beginning, it's a tough one to do, but what we have found, especially with the lead states, is the more we worked with it, the more comfortable people got, and the more they went, oh, okay, I can kind of see where that's coming from. And it really does allow you to be able to start constructing a rubric once you start looking at your assessment based on what's in those what Joe's going to talk about in a minute, or the foundation boxes. On the interactive side, if you want to go to that, you actually, as you mouse over the performance expectations, it actually pops up and shows you the practice and all that. But it's depending on how you want to see it. About half the people like that, half the people don't. So we got a button, you can turn it off if you want to. But the architecture is something that I think is really innovative, but I also think it's something that we're going to have to help people get comfortable with.
Okay, so we're going to help you try to get a little bit comfortable with this, and then this afternoon, your smaller groups will actually take you another step further on making you comfortable. So I actually want you to turn to the topics. There's a couple different ways to raise the performance expectations. One way is by topic, and so Michigan is actually using the topic arrangement. So I want you to find the tab that talks about topics, And then I want you to go to page 40 in there, because what I did is just for presentation purposes, I just abstracted out a part of it. But I actually want you to see the whole thing, right?
So Joe, as far as the topics go, the reason why you can rearrange these in all kinds of different orders is because there's internal coherence in the document. And the reason that works is because they are originally done as progressions. So it actually allows teachers to be able to rearrange them in a million different ways that suit their needs. And the state of Michigan just happens to like the topical arrangement. And that's fine. We don't care. Just as long as you do it.
Okay, so I want to make sure that everybody is on that page. And then we're going to go a step deeper. Okay, so let's look at this. These three boxes at the bottom, these are called, you should look at them in your page. I know they're not color coded, but because of money, but these are the three foundational boxes. The practices are always they're always blue. The disciplinary core ideas are always this orange color, and the cross-cutting concepts are always this kind of greenish color. And if you read the standard, right, so I'm going to read the standard for you. Develop and use a model to describe how the total number of atoms does not change in a chemical reaction, and thus mass is conserved. What you should be able to do is actually go down to the foundation box under scientific practices, and you'll be able to see what practice is actually being used, and it's identified because there's a link back to it. So you should be able to see there MS-PS1-5. And that tells you that this develop a model to describe unobservable mechanisms is actually what we're intending up in that performance. Otherwise, it could be something slightly different. The same thing is true under the disciplinary core idea. If you go down and you read it a little bit, it should say, MSPS-5. I think I actually cut something out here. But these are the two ideas which are actually related, the disciplinary core ideas that are related back up to the performance expectation. Similarly, if you look at the macroscopic, it should, again, I typed this wrong, sorry. This should say MSPS1-5. Again, it's the macroscopic properties are related to the nature of the microscopic and atomic level structure. So it links back up. You should be able to read this, and it takes you back up to your performance expectation. So that's how you can find what the practice is, what the core idea is, and what the cross-cutting concept is.
Online, you can click buttons for color. And so like if you can click and show practice with DCI, disparate core idea, and you'll see blue is the practice, and you can see develop a model would be blue. And if you moused over it, then the language in that blue box actually pops up. And then if you wanted to see the content, it's the orange. Then you click another button that can show you practice and cross-cutting. We can't do all three because the content and the cross-cutting overlap so much that the only way to fix that would have been like a zebra font of like orange and green, and that just didn't look really good. So we had to click, and of course we have people who just don't like color, so there's also a black and white button. But it actually does help you to look at the interactive site. You can actually see those connections back and forth.
A couple of other really important pieces of information that are on this page. Every standard will have, it may or may not, but they'll have a clarification statement. So it provides just a little bit more information about what that standard's all about. So you always want to look at the clarification statement. And then also there could be, but not necessarily, an assessment boundary, which basically means what's not in, what doesn't count for this. That's what an assessment boundary is. So it gives you just a little bit more information. So when you read one of these, you always want to look for the clarification statement. You want to look for the assessment boundaries. Now, there's a little bit more information.
If you also leave that completely, can I say one more thing about that?
Yeah.
Just so you know, when we went into this, we did a study of the top 10 performing countries in PISA. And one of the things that came out was that those top 10 countries use a lot of examples and a lot of clarifiers. So those two red statements came from lessons learned in the international community. And I have people all the time say, well, if you just written the standard clear enough to start with, you wouldn't need a clarification statement. And I'm like, okay, well, you go write me one and you give it to me. And, if it's good, we'll use it. And there are times you can do that, but just like Lay's potato chips, sometimes you can't eat just one. Sometimes you just can't get by with just one sentence. You need one more. The other thing about the assessment boundary, just to remind people, is this speaks to large-scale assessment. If you're teaching a group of gifted and talented students, that shouldn't limit you. But you should be it gives you the perspective of, okay, the average kid doesn't need to go there, right? I mean, it's more information for you, but it's also not meant to limit kids. It's actually meant to be something that when large-scale assessment is developed, it's clear you don't test this.
There's also also other things in these boxes called connections to the nature of science. So you can look, and one of the appendices is also a nature of science appendices. Over in the green box, and Stephen, I don't remember what this one is, these are also connections to other engineering. Do you remember engineering what?
Connections to engineering, technology, and society.
Right. So if there is one, there isn't always one. In this case, there wasn't one, so it's not here. Down, which you can't possibly read this. I can't even read either. I gotta go here so I can read this. So these are connections to other DCIs. So it tells you what other DCIs this is connected to. And these are articulations across the different grade bands. Like what's it connected to below and what's it connected up to above. So these, even though it's a little hard to read these things, they're really critical. Now, even further down, this is why I wanted you to open up your book. Even further down, you can now see connections to Common Core standards, both mathematics and to the literacy ones. So that's really important. So there's a lot of connections that are being made, both within the core idea, within the performance expectations themselves, what's it connected to before, what's it connected to after, as well as connections to the disciplinary core ideas, as well as connections to the Common Core. So that's how you read one of these. So the architecture is a little bit, you got to get used to it, but once you get used to it, it really has lots and lots of information that's very informative and can really help you understand what's going on. And you can write down questions if you have questions, we can answer them later. Okay, so probably the other really important part about the framework that we need to just talk a little bit about is this idea that understanding develops across time. And this is actually very different from us as a science teacher. Because we often thought that, when they came into my chemistry class, I started from ground zero. We studied what matter was. I assumed in my chemistry class that they didn't understand what matter was, and so I had to teach it over. In fact, it must drive kids nuts, because they learn about what's matter, occupies, space and has mass in 3rd grade, they do it again in 7th grade, 9th grade, again in high school chemistry, right? So that isn't anymore. The idea is to go deeper all the time, right? And that I have to actually rely on people before me actually helping my kids develop some pretty sophisticated understanding. That standard that you just looked at, this standard is a middle school standard. I, as a high school chemistry teacher, should assume that kids are going to come to me understanding that when a chemical reaction occurs, the molecules interact, and the atoms in those molecules interact to form new things with new and different properties, and that they can use that idea in a variety of different situations. And so the only way they're going to actually be able to develop that understanding, I'm going to assume they're coming to me so I can take them a step further, is that in elementary school, they actually had to do a lot of wrestling with what matter, what it meant, and what it's all about. In middle school, we really have to help them develop those ideas so we can take it this next step further. And so if we really want to have students leave our classrooms in 12th grade with really sophisticated understanding that they can use on the job and at college, we really have to think about ideas developing across time. And these are the progressions. And so there's one of our tabs, or actually I'll say I think it's listed later. There is a tab that shows actually progression of the core ideas across time. There's a tab that shows how the various other, how the cross-cutting concepts develop, how the scientific practices. And this afternoon, there'll actually be a session talking about all the various progressions. One thing, and I guess I stressed this already, these ideas just don't magically appear, right? It really depends upon our instruction. What we do in our classroom means more than anything with respect to students really developing the kind of in-depth understanding that we want kids to actually have. So here's that little slide. Remember I said we share slides? This is actually this idea about building understanding over time. And these are the appendices you can look at. So if you look at Appendix E, those are is a progression of the ideas developing across time. So you want to look at Appendix E. So indeed, the next generation of science standards are different. And again, because of this blending, because of the depth, because of this notion of developing across time, I want to again stress that these are what kids are actually going to be assessed on. They are not instruction. Right? We have to just realize that they're not instruction. So, what are some implications? We could think of these performance expectations as not telling us what we're going to do in class, but they have to guide us. Right? They have to, because we have to know we have to go there. There's something we have to be shooting for. We have to be guiding what our instruction does. And then, of course, if it's guiding our instruction, it's certainly got to state very clearly what the assessments are going to be, because that's what they are. They're what kids are going to be assessed on. So you can almost look at this statement, develop and use a model to describe how the total number of atoms does not change in a chemical reaction and thus masses are conserved. You can almost stop and think, well, what are these state tests going to look like? What are these national tests going to look like? Well, if this is what they're going to be assessed on.
There are no national tests.
Well, not any national, whatever they are. No national tests. These tests that you buy from these larger groups, what is it going to look like? Well, it's going to be pretty clear. The kid's going to have to develop and use a model. That's number one. It's not rocket science, right? That what the kid could be assessed on is developing and use a model, and in designing and using that model, they have to very clearly specify that in a chemical reaction, the total number of atoms does not change, but they simply rearrange, and thus mass is conserved. That's what the assessment is done. We're going to have to design assessments that look like that. Now the question really becomes, then, what do we do in instruction to help our students get there? That is indeed the critical question. What are we going to do? So, I know you probably can't read this, it's okay. This is actually, it was such an important document that it's right after your agenda. So if you open up your books, this should be the next handout after agenda, is that correct? Yes, okay. This is our, and Sue will actually introduce these people when she comes up here. This is a document that a number of people use to actually develop some of the breakout sessions. And it actually is really critical for us. So you can actually, as I'm talking, you can actually refer to this document. Yeah, this is sort of like on the back of that document. Yeah, if you turn around, you'll see the listing. Right? Yeah, it's on the front part too. So you'll notice when you look at that document that the front part tells you how to read. It sort of goes over what I just finished. How do you read a performance expectation? I want you to add one important word, right? This is sort of a work in progress, and we're going to just add one word to this document, so everybody should take out a pen. And in the back, you should find this thing, developing lessons to meet performance expectations. And after the first bullet, the first point, where it says select related performance expectations, typically for one topic area, I want you to put in parentheses bundling. Right? That's what bundling means. It means we're selecting more than one performance expectation. It could come from several topic areas, but typically it comes from one. maybe 2. And so I'm not going to sort of walk you through this entire process. And in this afternoon, what's going to happen is people, your breakout sessions will actually go in depth into how you really go about doing this.
You know, one of the things that I've talked about a lot is that the standards are really about a common ends but an uncommon means. And so this whole idea of bundling, some of it is what makes sense to you as a teacher. Because it's been my experience that if you try to get me to teach something that somebody else created, I usually didn't do a very good job of that. And so the pressure was really on the writers in the states to develop a document that was really coherent, that would allow the flexibility for teachers to be able to bundle them in multiple ways. So that's a lot of where your flexibility is going to come.
Okay, so we're going to walk through this process. So step 1 is select related performance expectations. Bundling, make sure you include that, bundling. And what that means is that you as a teacher, you're going to have to put some things together. You're going to have to look at where what you're doing. If you're a middle school science teacher, you're going to have to put these things together. So we're going to use the topic view to identify performance expectations. And I'd really like you to go back to that page that we were at in the performance expectations, because we're actually going to make use of that. Again, I'm a chemist, but I picked middle school because I figured we can go a little bit up, a little bit down, that's fine. So if you go to that page, I actually picked, so this is page 40 of middle school chemical reactions, I actually picked 2 of the performance expectations from that page to sort of bundle together. Maybe I could have picked more, but for purposes of illustration, I just wanted to sort of work with 2. So the 2 I picked on was what we already started with. So we have develop and use a model to describe how the total number of atoms does not change in a chemical reaction and thus mass is conserved. And the second one I picked was analyze and interpret data on the properties of substances before and after they interact to determine if a chemical reaction has occurred. So these are the 2 things I picked, right? But I just selected them. The next thing you really need to do is just like we just got done reading them very carefully, you have to go and do that again. You want to read and study the performance, step 2. Read and study the performance expectations, the clarification statements, and the assessment the assessment boundaries. It's critical that you do that. And when I say read, what that really means is going to step 3, where you want to go down to those foundation boxes, and you want to identify the core ideas, and read what that core idea really means. You want to really understand that practice, and what that practice really means. You want to understand that cross-cutting concepts that are coded to all of those performance expectations. So if we could, I think you have to, can someone up there hit this backwards arrow? This arrow is working. Okay, so this, nope, that didn't do it. Didn't do it either. You have to put the cursor right on there. Put the cursor on there. Click it.
This one?
So you want to. This is where you want to go to, right? So you want to go to this page, and you really need to carefully study these boxes. Now, I'm going to encourage you when you're here, you really want to go and look at the entire middle school practice related to modeling. It's critical, right? So go open up your book right now. Go to it's Appendix F, find modeling, and find the middle school section on practices. So what you want to do is you want to read that top section, which has some nice narrative about what it means to modeling, and you also want to read that section You know, in this case, we're doing middle school. What does it mean to do modeling in middle school? You might want to look a little bit about what happened in 5th grade up to 3-5, because what are they coming there with? You might want to look to what are they going to have to leave you with? What are they doing in high school? So it's very important that you study that page very carefully. It's not just reading it's not just reading develop a model to describe underlying unobservable mechanisms. It's really trying to develop an understanding of what that practice means. And so in the next generation of science frameworks, or in NGSS, we really try to give some understanding of what that means. We didn't write this document, the practice document, in one day. I tell you, it went through numerous revisions.
Yeah, and actually, one of the biggest things you can be doing right now, you know, nobody expects this to be, you know, even if Michigan adopts this month, you know, no, I don't think there's any plans for y'all to actually be implementing them next year. But one of the things you can do is start understanding the practices. And you need to know that takes time. I mean, Joe will tell you, Joe and Melanie both will tell you, even as late as, you know, the last 3, 4, 5 months, we were still having at times debates about the difference between explanations and argument. It really takes a lot of time. We actually spent 6 months before we ever wrote the first performance expectation, learning of how to speak about practices in a consistant way. It's a bit of a challenge because they are very new in a lot of ways.
You want to do the exact same thing with your disciplinary core idea. But in this case, this is where you really want to open up the framework book and go and read that section in the framework book that's related to that disciplinary core idea. This is a little snapshot of all the rich information that's actually in the framework book. So that's why that book is so important. It's free. I mean, it's nice to maybe have a paper copy, but you don't need to. You can always read it online. It's free.
If you want a copy of it, I think the plan is that they're actually going to sell companion as a package, the NGSS and the framework when they finally print that. Just a little side note, the NGSS is the first document that National Academies Press has ever published that was not done by an NRC committee since Lincoln commissioned them. That's not a joke, it's actually true. They have never published a document that the NRC itself did not publish. So that kind of tells you that we did pretty good about meeting their expectations.
Same thing is true with the cross-cutting concept. This is just a little blurb about what the thing really means. In this case, you want to go read the framework book on cross-cutting concepts, but also go to the appendix on cross-cutting concepts, which again is in your book, and read what is meant by, you know, patterns, and particularly see the application of that particular idea. So it's just critical that you do that. Now in back, if you could click this back arrow. You got to go down a little bit. Good. So now that takes us to step 4, right? So now we look more closely at the core ideas of PEs. What understandings need to be developed, right? So we studied those a little bit. We have to kind of learn. We want to say to ourselves, what do kids really have to know to get there that's not necessarily directly obvious? What content ideas will students need to know? What must they be able to do? So you're going to, as I said, you're going to examine the disciplinary core idea. You're going to, in the framework, you're going to look at the DCI progression chart in our books. That's really important to look at that. You're going to examine, that's Appendix E. You're going to look at the storyline, right? The storyline is really important. And if you go, in this case, to page 33 of the topic view, you'll see the storyline related to middle school chemistry, physical science, of this idea. And so those storylines basically tell you how the understanding should unfold. So it'll give you a little bit more insight in what we're really trying to look for. So that's on page 33. So I know this is really a lot of work, in time, but that's in some respects how you'll develop an understanding of this. You know, later on I have a slide, if I ever get that says, this is not evolution, it's revolution, right? We're seeking our kids to have deeper knowledge. We're seeking our kids to be able to do more. And that means we actually have to know and do more as well. So if you could click on this little green button now. Okay, so if we look at this, these were the two performance expectations I picked. You might want to stop and just ask yourself a question, just like I did. In order to do this, what are some things that kids really have to know, right? And what do I have to focus on in my classroom in order to get to there? So you can just sort of, ask yourself, look at those two things and say, well, in order to be doing this, do I have a performance expectation that says, they know about properties? No, there's nothing that says that. If you look at all the performance expectations, there's not one thing that says kids will do something related to properties, right? But it's here. That means that somehow in our classes, kids are going to have to develop this understanding of what properties or substances are. You'll notice that chemical reaction is used in both of these, but there isn't anything specifically about it, right? So we have to make sure in our instruction that we work with them on those ideas. All that is still there. It's not that we tell them those ideas, right? We have to actively work with our kids to build those understanding, but they have to know all those related ideas. You can go back now. Okay, so that takes us through step 4, right? So it's really getting to know the document and really understanding what's there and what's not there. Step 5 is to select practices that work with the core idea. Because in our instruction, what we're going to have to do is we're not going to just have kids just do modeling all the time. We're actually going to blend the other practices with those disciplinary core ideas so that they have more experiences with those core ideas with different practices. That's really going to help the kids really understand those disciplinary core ideas. It's really going to help them understand the practices. So then as science teachers, we're going to have to ask ourselves, what other possible science and engineering practices can I use? Right? So I selected construct, explanation, and design solutions. I selected analyze and interpreting data. That actually happened to be one in one of the performance expectations. I selected construct models from evidence. That was also one of the performance expectations. And I selected asking and refining questions. So I think, and I could be wrong, but at least for my instruction, I thought those would work particularly well to doing other things when I bundled those two performance expectations, other practices with those core ideas that those two things have that I could use in my classroom. I might, you might say, oh, Joe, how come you didn't select arguing? It's a good question to ask, but in my class right now, I thought, no, I'm not going to do that. I think these work particularly well. So, with that then, we have to develop lesson level expectations. Performances that we as teachers are going to expect our kids to do in our classrooms. Maybe these are formative assessments. These are the various activities we're going to engage them in. These are going to be our goals. You can think of lesson level expectations as our learning goals expressed in terms of performance or knowledge in use. I like to call them learning performances. It's just my language. And the reason why I like to use the word learning performance is because it focuses on what we want the kids to learn. So they're a learning performance versus a performance expectation, which is what they're going to know at the end of instruction, right? So we have a learning performance, which is guiding our learning, which we are going to create as teachers, versus performance expectations that have been created by the Next Generation Science Standards, what kids are going to be assessed on. So learning performances are lesson level, and you want to think of these as learning goals. I think that's really critical. They're guiding our learning. Again, just like the performance expectations are defined in terms of something cognitive, some kind of knowledge and use, our lesson level expectations should also be developed that way. And I'm going to stress, this is going to be really hard for all of us. If people say, well, Joe, why can't I just use the word know? Why can't I just use the word understand? Because if someone says to you, the student will understand X, right? What does that actually mean? What does that mean to understand? What does it mean to know? The term is just too vague. I don't know what it means. I don't know what I would assess the person on. So we avoid the term know and understand, and rather I'm going to encourage us when we design our lesson level expectations that we use the scientific practices. That's why we selected them, and we blend those with our core ideas to make our lesson level expectations. But avoid the word know. It's really tempting. I want kids, when they leave here, to know what a chemical reaction is. And I would come back to you and say, well, what do you expect them to be able to do with a chemical reaction? Right? That's the whole notion of what it means to have knowledge and use, and that's the whole way in which performance expectations were actually designed. So, and these are very important because unlike the performance expectations, these actually guide our instructional decision. They guide what we're going to do in class. So they're very, very different than the performance expectations. So, okay. So how do we create one of these? Really similar to what we saw before. It's not any different. You're gonna take your core idea. In this case, each pure is a little bit more abstracted of it. Each pure substance has characteristic physical and chemical properties for any bulk quantity under any given condition that can be used to identify it. I'm going to blend that with practice, construct scientific explanations based on evidence, and I'm going to blend that with a cross-cutting concept, cause and effect, and that then creates this learning performance, our learning goal. Develop a scientific explanation that different substances have different properties. That guides what I'm doing in class that will help me meet those two other formal performance expectations. It itself isn't a performance expectation itself, it's just a small nugget of the performance expectation. Because in order for kids to really know those two, they really have to have an understanding of what chemical properties are. And if they don't understand that, they simply aren't going to be able to do the part related to when a chemical reaction occurs, you get new substances that have different characteristic properties. So I broke it down and said in my instruction, I'm going to engage my kids in actually doing something, construct explanations about different substances that have different properties. Just like Stephen, here's an example of an assessment that I might use in my class. This is a lesson level assessment, right? So this lesson level assessment says students construct a scientific explanation that includes a claim about whether two items of the same substance or different substances, evidence in the form of density, melting point, solubility, color, and hardness of a substance, and reasoning that the different substances have different properties. So that's my classroom assessment, or maybe it's a formative assessment that I want to give my kids. They either have a table or they collected the data in class, and then I expect them to write a scientific explanation in which they're giving me a claim and the evidence and the reasoning behind that. So that's where that would take us to. And again, it's not either one of the performance expectations, but it's a step in getting them to those performance expectations. So I'm going to stop there and see if Stephen wants to chime in on anything at all. Nope.
Yeah, the only thing I'll say is, you're getting a lot of information today. And hopefully it's starting to resonate with you why I keep saying you have the courage to be patient. Okay, this is not going to be something that, in fact, with most of our states, I think we're looking at 3-4 year implementation time. And, you know, my biggest advice to you is this: don't try to bite off the whole apple. You know, you can start doing some of these things in your classroom, but find one thing, focus on it, and do it well. You know, don't try to do everything at once. Administrators, be supportive of your teachers in that endeavor and don't push them to do stuff that they're not ready to do. You really need to think this through and be very deliberate and have a plan. Don't get caught up in all the stuff. The stuff will come if we just are thoughtful.
So this is actually our dream, right? And it's not just, I have modeling up here for an example, simply because it was sort of the main performance expectation that I started off with. But imagine that in kindergarten, our science teachers started to engage our kids in modeling. It's going to be very descriptive, but the kids are going to actually have a model to explain a host of various kind of phenomena. And they're going to do it around these core ideas. So this is not doing modeling like Stephen mentioned what we used to do with paper towel activity, where we just made it, no content in it, right? This used to drive me nuts as a science instructor because there wasn't any content. So, but this is actually taking a practice, actually blending it at a very early age, some of the content, and engaging kids in modeling. And then they go to 3rd to 5th grade, and they continue to engage in modeling. And it's not just creating a model, but they actually have evidence behind that model, and they actually realize that when they get new evidence, new information comes in, they actually change their models. They go to middle school, and we take that another step further. They're still engaging with the content, with modeling. They realize that, oh, my previous models simply don't explain this rich enough. That goes a step further, in which they take it even deeper in the high school. Imagine what that student would look like. If in the K3 areas, kids developed a descriptive model of matter. So they knew that solid things were hard, right? There are some things that are liquid that can evaporate. And then when they get to the 5th, 6th, 7th grade area, they start to just develop a particle model of matter. So they had a descriptive model, then they go to a particle model of matter that can actually explain a lot of phenomena, like phase changes, for instance. So they can explain some things with this particle model, not everything. They can't explain why atoms come together. They don't understand why things are sticky, but they can use this particle model to explain why you can have 3 phases of matter. Then they get to high school, and that model actually becomes richer because now they understand what that stickiness is. So think about if that's how school was structured, that we as teachers from the very early ages help kids to develop these models. Think of what they would be like and they always had evidence from it. They would be very different learners. They'd be very different citizens than the individuals we have, that we are doing today. Not that we're doing a bad job, but we live in a different society today. Our kids are going to have the knowledge and the knowledge use that's going to be demanded of our children is much greater than what actually was demanded of us. Everybody has to have a much deeper understanding of this information. So my dream is if we could really take what we have in the next generation of standards and really build it across time, that our children will look very, very different than what they look like today. So, business is not the same. I think we're in a very different situation. The framework is very different. Again, I want to really encourage you to look at the framework. NGS is different. These aren't, Stephen said this point, they're not written like standards were before. Hopefully, I helped you understand a little bit about the architecture. And not everybody agrees with me on this. Again, this is just me. This is revolution. This is not evolution. This is not a small stepping stone. This is going to require for us to be very different, do very different things in our classroom. Now, it's not necessarily just like, it doesn't have to necessarily happen overnight though. But 5 years down the line, being that patient person I am, I'm supposed to laugh, being that patient person I am, in 5 years, we will have very different classrooms. Maybe not next year, but in 5 years and 10 years, we will be in a very different place. And our children will be in a very different place. And, we will, so that's what my hope is.
We have over 50 companies who have signed a letter of support for the NGSS. So that speaks to the fact that business is changing and they're expecting us to change. And then I just have to say, NGSS is different, as we used to say in Georgia, these ain't your mama's standards.
So I want to encourage you, as Stephen said, I gave you lots and lots of information. So I want to encourage you to write some questions down. Sue is busy sorting them as we speak, but it's important to get these questions out and bring them up to Sue. I also have my contact information down there in case you want to contact me, and I'm a pretty good emailer. Sometimes I miss an email now and then, but there's people around the room that will tell you that I typically email back, so feel comfortable emailing me. And with that, I actually want to, first of all, Sue's going to do more of this, but I have to go with thanking these people as well. All the people that have been walking around helping you, they have been really troopers the last couple of weeks, really putting together these afternoon sessions. And so they really deserve a thank you from me, from Sue, from all of us, because without them, we wouldn't have what's going to happen this afternoon.